All right, motion word problems part 2, looking at headwind and current. So first problem today. In still water, Peter's boat goes 4 times as fast as the current in a river. So they're giving us his rate of that sentence. They're trying to tell us if he were in just like a lake where the water doesn't have a current, his boat would be 4 times faster than a current. Now he's actually in the river with the current, and he takes a 15-mile trip up the river, and he returns in 4 hours. We're going to find the rate of the current. So the key step with this general type of problems is this. When we create our chart, rate, time, and distance, in general, we don't want to make like Peter's rate and the current's rate. That's not going to work very well. What we usually want to do is we want to say like there and then back. And this is really the key step for understanding a lot of these types of problems. Now in this particular problem, it's really the total column that's going to help us out the most. But in general, we're going to think of Peter as almost 2 different people. Because if you think about what's happening, when he goes up the river, his speed is slower, right? So he's sort of like a different traveler. Then when he comes down the river, his speed is faster. Because when he goes up the river, his boat might say it's going 15 miles an hour, but if the current is 5 miles an hour, he's only going 10 miles an hour up the river, right? And when he's coming down river, if his boat says 15 and the current is 5, he's really going 20 miles an hour down the river. So that current changes his rate, and it's going to change his time as he goes up and down. And it's the same thing. Sometimes you'll see a problem with headwind, like a plane flying, and this is technically how those plane problems all work in real life. When a plane goes from like Chicago to New York, I don't actually know which direction is faster, but when it goes from Chicago to New York and then turns around and flies back from New York to Chicago, in one of those directions the planes will be facing a headwind. So it'll take longer, like let's say it takes longer to go from Chicago to New York. But then the other direction it will have a tailwind pushing the plane. So even though the plane can go like 600 miles an hour, that headwind and tailwind will make one trip faster than the other trip. So in our chart, we're generally going to think of the trips as going there and coming back. But in this case, they really only talk about the total. So let's try to fill in the total. We know that his boat goes 4 times as fast as the current in a river, right? So we could say that his rate going there, this problem is actually kind of complicated. So his rate, like if we were to just think of the rate of his boat, it would be 4, and then let's just use C for current. His rate is 4C. So when he goes up the river, his rate is going to be 4C minus C.
So would that just be 3C?
Yeah, which would just be 3C. When he's coming down the river, his rate is 4C plus C, because coming down the river we add the speed of the current to his speed, so it would be 5C. The time is 4 hours, distance is 15 miles each way. So the total distance would be 30. So the tricky thing about this problem is that we're going to end up with two variables. Because we don't know, we can't assume that it took him 2 hours to go upriver and 2 hours to go downriver. In fact, we know that going downriver is going to be faster, right? So we're going to end up having another variable. And it doesn't matter how we do this, but let's say it takes him t hours to go up the river. To come down the river, it's going to take him 4 minus t hours. Okay. So here's what we can do. We know that 3c times t has to equal 15, right? We also know that 5c times 4 minus t has to equal 15. Right? So this is actually a much more complicated problem than I thought it was. All right. No. But this general setup will definitely work. So once we get to this point on your homework, the equations will be much easier. But I don't know, I grabbed this problem from something that I had and I didn't realize how complex it was. So there's a couple ways that we could solve this. For example, I'm trying to think if it's worth showing you guys how to solve this actually. I think it's not. Let's just stop there for now. We could eventually come back to this because we will eventually learn how to solve this. But if you understand the setup, that's good enough for now. Okay. So let's look at a different problem that the solution part is easier. So we'll stop there. We'll forever wonder about the speed of Peter's river and his boat. There's probably actually a different way to solve that problem if we were to look at it. But all right, here we go. So this one's a little simpler. A cargo ship traveling with the current went 180 miles in 9 hours. On its return voyage, traveling against the current, it took 18 hours to travel the same distance. chart. Just remember we're going to say like going there and coming back. Alright, so going there, we still don't actually know the rate,
Well, we could figure it out, right?
right? Because, yeah, but we can actually figure part of it out. So he went 180 miles in 9 hours, right? So we could say 9 hours and 180 miles. Yeah. Do you have something to say? Okay. So there's a couple ways we could fill in the rate column. I'm going to do it like this for now. I'm going to say the rate going there is the speed of the boat plus the speed of the current. Then the rate coming back is the speed of the boat minus the speed of the current. And we know that coming back, took 18 hours to go 180 miles. Right? So there's a couple ways that you could solve this from here. I'll show you one of them. So we know, for example, that if rate times time equals distance, the overall rate would just be the distance, 180 miles, divided by the time, 9 hours. Right? So if we took 180 divided by 9, we would know that his rate going there is 20 miles per hour. And the other one, the rate coming back, 180 divided by 10, is 18 miles per hour.
No, it would be divided by,
Divided by 18.
it would be 10 miles.
Oh, sorry. Now I don't know why I'm having trouble looking at this. Okay, 18 is the hours, right? I was like solving it in my head and just writing the wrong thing. So 180 miles divided by 18 hours is 10 miles per hour. From this point, there is like an algebraic way of solving this, but if we think about what we have, we know that he has like the speed of his boat. The current has to be the same. The current's going to stay the same.
So
Did you see the answer?
speed of his boat is 15 miles an hour,
Mhm.
and the current is 5 miles an hour.
Right. So the speed of his boat has to be 15. It has to be halfway in between these two. Right? So the boat speed is 15 miles per hour. And then the current, when he's working with the current, 15 plus 5 is 20. When he's going against the current, 15 minus 5 is 10. So the current is going 5 miles per hour. And I think at that point you can kind of just look at this and say, oh yeah, I can figure out the speed of the boat as being halfway in between and the current is 5. Right? It's half of that distance. I don't think we need to go into algebraically how you could solve that. Alright, let's look at one more problem. That uses headwind or current. All right. All right. Barry is flying a model airplane at 20 miles per hour with a tailwind. 45 minutes to travel from school to Nate's house. Where it drops off an important package of math homeworks. The return trip takes 1 hour. But the plane is, oh wait, sorry, this, I think I got this wrong. This is
Well, that one makes sense because it takes longer when it has right?
yeah, this makes sense. But the plane is traveling with a headwind.
I'm not sure the math one works away, because dropping the package
It's
How?
lighten up the plane so
Fast.
it travels faster.
Is
Just imagine that it's like it weighs 0 pounds. It probably is.
So here's the thing you have to know to solve a problem like this. It's the same setup, but when I say that the plane is traveling 20 miles per hour in this case, the problem actually said, I didn't want to write it out, like on the speedometer, right? So it thinks it's going 20 miles per hour, but it's not, because it has a tailwind. So just to clarify, and in the problems on the homework, it is a little bit clearer, like it will say 20 miles per hour according to the plane's speedometer, right? So the 20 miles per hour is the speed of the plane without the headwind. So let's set up our chart. Rate times time equals distance. Rate times time equals distance. So again, we're going to say going there and going back. Now we're going to assume that that 20 miles per hour, since it's the only speed they gave us, is just the constant speed of that plane. So the speed going there has a tailwind, so it's going to be 20 plus, I'll just say W for wind. Coming back, though, the speed is slower. It's 20 minus the speed of the wind.
So there it's, and the time is 45.
The time here, now here's another trick. Can I do the time like this? 45 and 1? It's 45 minutes and 1 hour. No. I have miles per hour. So I really want my times to be in hours.
So it could be like 45 out of 60.
Yeah, so I have to convert 45 minutes into hours. How many hours is 45 minutes? Well, I know that it happens to be 0.75.
Oh yeah.
It's 3/4 of an hour, right? 45 minutes is 3/4 of an hour, so it's 0.75. So I have to kind of watch my units. And then the distance, I don't actually know in this problem. But, does it matter?
No?
What I know is that this distance is the same as this distance. So again, we sort of have two variables here. But this problem is going to be a little even easier than the other ones. So technically what I can do is the same thing we did to solve the other problems. I can say, oh, the distance is the rate times the time. So it's 20 plus W times 0.75. And this one is 20 minus W times 1. So it's just 20 minus W. And then I can think, oh, the distance going there has to be equal to the distance going back. So, the 0.75, I'm going to write it in the other order. 0.75 times 20 plus W has to be equal to 20 minus W. This distance going there is the same as the distance going back. The distance from my house to the school is the same going there and going back. It just takes a different amount of time because of the headwind or the tailwind. Alright. So now I can solve this. You guys know how to solve this one algebraically. 3/4 of 20 is what? 15. Plus, we'll just say 0.75 W equals 20 minus W. So I would subtract 15 from both sides. And while we're at it, let's add W to both sides. So I have 1.75 W equal to 5. You could either get out a calculator at this point, or you could divide, or we could convert this into a fraction. Right, that's 3/4 plus 4/4. So I know I have 7/4 of W equals 5. And then I could multiply times 4 and divide by 7. W would be 27. So we could say the speed of the wind is 27, or we could get out a calculator and write that out as a decimal, miles per hour. Let's just see what it is. 20 divided by 7. So it's 2.857142857 miles per hour. Questions on that one?